Hello, in this video, we're going to be solving this question, which is about the solution to a system of linear equations. So it says, determine the values of k for which the system of equations given there does not have a unique solution. Okay, now, you might remember that the condition that we're looking for a system of equations to not have a unique solution is when the determinant is equal to 0. So what we need to do is represent these equations as a matrix, and then we need to evaluate the determinant of the matrix and set it equal to 0, because it's only when the determinant is not equal to 0 that we do have a unique solution. So the fact that it's telling us we do not have a unique solution means that the determinant has to equal 0. So representing the matrix in matrix form, we have 1 minus 3, or rather the system of equations in matrix form. We have 1 minus 3, we have k, we have 1, we have minus 1, we have 6, we have minus 5, and we have k minus 1. Okay, so that's our matrix, and that's times by x, y, z. And that is going to equal minus 7, minus 5, and 1. Okay, so that's our system of equations represented as a matrix. So we've now got to evaluate the determinant of this 3 by 3. Okay, so our 1 minus 3, 2, k, 1 minus 1, 6 minus 5, k minus 1. And we need to basically evaluate this and set it equal to 0. Now, if you remember, we have a pattern for our when we're working that we need to follow pluses and minuses when we're working out our determinant, and we have the pattern that we need to follow is it for the first line is a plus, a minus, and a plus, and we basically take each term and we multiply it by its corresponding minor. So we're going to have we've got a plus for the first term, so that's going to be positive 1 times by its minor, and the minor is 1 minus 1 minus 5k minus 1. Then we've got a minus, and then we're going to basically have this next one, so we want to eliminate that column and that row, and we've got minus 3 there. So we've got minus 3, and the corresponding minor is k6 minus 1 and k minus 1. So we have got k, 6, minus 1, and k minus 1. And then finally a plus, and the last term is a 2. We eliminate that row and column, and the corresponding minor is k6, 1, minus 5. So k6, 1, and minus 5. Okay, perfect. So we're now ready to evaluate our determinant. Okay, so we're going to have positive 1 times by k minus 1. So that times that minus that times that is going to be k minus 1 minus positive 5, which is just minus 5. Then we're going to have a minus minus comes together to make plus 3 times by k minus 1. And then minus minus 6 is going to be plus 6. Then the next one is going to be plus 2 times by minus 5k minus 6. Okay, so that is correct. So now we just got to remove our brackets and collect like terms. So we have got k minus 1 minus 5 is minus 6, and we're going to have plus 3k squared minus 3k plus 18. And then we're going to have minus 10k and minus 12. So let's collect all this together now. So we're going to have 3k squared. We're going to have minus 3k minus 10k plus k is minus 12k. So there we go. That's those dealt with. And then we've got here plus 18 minus 6 minus 12. That cancels out. So that comes to 0. So therefore, that is our determinant. And we need to set this equal to 0 in order for us to not have a unique solution. So if we're going to solve this, we can take out k as a factor, giving us 3k minus 12 is equal to 0. which means that either k is 0 or 3k minus 12 is equal to 0. So 3k is equal to 12, which gives us that k is equal to 4. So the two values of k for which the system of equations does not have a unique solution is that k is equal to 0 or k is equal to 4. So that's part A done for our 4 marks. Okay, part B. Given that k is in fact equal to 5, by finding an appropriate inverse matrix, solve the system of equations. Okay, now I think for this number of marks, they're not going to expect us to find the inverse of the matrix fully longhand. I think it would be sufficient just for us to represent the matrix times by x, y, z is going to equal -7, -5, 1. And we can just use our calculators to calculate the inverse in a moment. So we're going to have the matrix, which again was 1, -3, 2, 5, 1, -1, and 6, now that we know that k is 5. 6 minus 5, and then we're going to have 4. Okay, so that is fine because k minus 1, yes. So we've got our k is 5 represented there. So that means that x, y, z, our unique point, is equal to the inverse of this matrix, 1, -3, 2, 5, 1, -1, 6, -5, 4, multiplied by -7, -5, 1, is going to give us our x, y, and z, our unique solution. And we can literally just program that into our calculator, find the inverse, put that into our calculator, find the inverse, which I'll do the details of how you enter that into your calculator more fully in another video. But when we do that, we find out that we get the following. 1 over 15 can come out as a factor, and we are going to end up with the following here. So this is going to be, our inverse is 1 over 15, and this is going to be -1, 2, 1. And we're going to have -26, and then -8 and 11, and -31, -13, and 16. So that is our inverse matrix, and we're going to multiply that by the -7, -5, 1. Again, it's perfectly fine to use our calculator to do that. Okay, and when we do that, we get the following. We get -2 over 15. We get 233 over 15 and 298 over 15. And that is our x, y, z. And we found the solution. So our solution to this system of equations is that x is equal to -2 over 15, that y is equal to 233 over 15, and that z is equal to 298 over 15. Okay, so that's that first bit done, B part 1. And then the second bit, interpret the solution geometrically. Again, in my experience, this is another part that often causes confusion. But in this case, we can only have an inverse to a matrix when there is a unique solution. And there is only a unique solution when the 3 planes meet at a point. So what we've got is that the 3 planes meet at a single point. So the 3 planes meet at a single point. That's our geometric interpretation of the solution. And that is how you would do that question on solving a system of linear equations. I hope that you found that video helpful, and I will see you in the next video.